Hello, today we have a new guest, Elias, a very talented programmer, business person, and he will be doing a presentation about actually a very exciting topic related to artificial intelligence. Elias, please.
Um, Thank you, Leb. Hello, everyone. I'm Elias, and today I will talk about the integration of advanced embedding technologies with the traditional text search mechanism. As everyone knows, we live in a world of inundated with data, so the necessity for precise, efficient, private, and meaningful text retrieval has never been more critical. So we will talk about the complexities of vector databases and embedding models. This is me. You can see in the picture. I am the founder of the company AI Monkey, which is a software development company that offers services based on artificial intelligence. I also have a startup called ECAI that is just a small prototype. So it's not out in the market yet, but we are thinking on releasing it soon. We are in demo stage with some few clients. I would like to give a special thanks to all this AI study group. I've learned a lot here, and I really want to thank everyone, especially Shareya for all her advice, and of course, Dr. Lev Selector, which has been an amazing tutor and a great person who has guided me so far, and I owe him a lot. So this presentation is dedicated to them. So we are going to start here with the core components of this that we're building, which are vector databases and embedding. So vector databases are a cornerstone in modern search and recommendation systems, handling the complexities of multidimensional data with finesse and precision. So these databases stand out for the ability to manage and query vector data, something that traditional relational databases aren't tailored for. But how do they achieve this heightened level of efficiency and accuracy? Well, I would say one word, high dimensional data. But what do we mean with high dimensional data? Because like, okay, we think in different dimensions, more dimensions, okay. But let's take that a step forward. So a simple analogy. Imagine a vast open field where every point on the field represents a piece of data. Now, in a simple world, we only need two things to locate that point. Maybe how far along and how far up it is, like coordinates in a map, right? So, but hold on. What if our data isn't just a point in that field? What if it's located above the field or buried beneath? Suddenly, we need more than just two measurements to find it. We need to know the heights, the depths too. And this is where we start stepping into the realm of higher dimensions. In the world of vector databases, we are often dealing with data that has many attributes, characteristics, or features. It's like trying to describe, I would say, imagine a sophisticated piece of art. It's not only about the colors or the size. It's about the texture, the emotions it evokes, the era it belongs to, and so much more. Each of these aspects adds another dimension to our data. Imagine that you have a painting, and if you would only have two dimensions, you would have, okay, so each little dot is a color, and you have coordinates, and you paint a smiley face. But what about everything else that a painting can transmit? How do we store that? And how can we make a machine learn about that? And embeddings, which on the other hand are the soul of the content residing in these databases. So embeddings play a role of converting text into numerical forms, vectors to be precise. These are not just arrays of numbers, but are impregnated with the rich semantic essence of the original text. Every word, phrase, and sentence, when transformed into an embedding, carries within the contextual meaning, the subtle nuances, and the integrated relationship that exists within the text. So these embeddings, high dimensional and complex, are what content-based search is not just a technical process, but an art form. So they enable the database to understand the meaning behind the queries. And that's, we are ensured that the results aren't just matching keywords, but they are contextually understood, and they are aligned with what the user intent. If I have a search and I'm searching something about Moses or open the Red Sea, he would understand the intention of what I'm trying to search, and he's not just looking for words that match. So I have this slide that is 3 pictures. And I know that Lev was very curious about what these pictures meant, so here I'm going to explain. So the King of Hearts, the one in the left, he exists solely in a 2-dimensional world. His movements are limited left, right, up, down. There is no concept of depth, no through or over. He's like a character in a drawing, forever bound to the surface of the paper. When he encounters an obstacle, there is no going around it the way we would do in a 3-dimensional world. He must have to navigate between the limits of this 2-dimensional existence, seeking paths that exist solely in the plane of his card. Every shape, every entity that interacts with him is flat and 2-dimensional as he is. He lives in Flatland. So the second image, you can see Flatland, which is a novel. It's called Flatland, a romance of many dimensions. So it's a satirical novella that was written by this guy called Edwin Abbott, and it's from 1884, I think. It's an old novella. But the story describes this 2-dimensional world inhabited by geometric figures. So women were line segments and men were like polygons, and everyone had like different numbers of sides. The narrator is a square. So then one day he travels to the 2-dimensional world and everyone is like lines, but then one day he meets a circle. But since he lived in a flat world, the circle for him is only like a little line, and he can understand that the circle is different than him, and the circle is actually a sphere, and he tries to teach him about higher dimensions. And eventually he comes to the realizations that there might even be more dimensions than 3, 4, or whatever. And when he tries to explain that to the sphere doesn't understand. So it's like a very interesting novella. And when I was thinking in understanding the complexity of multi dimensions and higher dimensional context, I believe that this novel becomes relevant and is still relevant. So also here we have the Mona Lisa, and I think that this is a great example of how just points in a 2-dimensional space with a color is not enough to transmit everything that all the information that that painting might have. Even though in the computer you are just displaying the picture, the Mona Lisa, the mysterious smile and deep feelings can be compared to complex data. Each brush stroke and color change is like a different piece of information, capturing unique parts of her expressions. Think of her smile, the way her lips curve, her eyes twinkled, and the gentle colors that flow her emotion as different points on a map. When all these points combine, they give a full picture, allowing for a closer look and better understanding. And this is similar to how technology and complex data with many parts is broken down to study and understand it better. So other thing that is important to do this, and how we create this embeddings and that fill these vector databases, we need to understand sentence transformers, which are tools that transforms text into numerical vectors. So these vectors capture the essence of the words, phrases, the overall content that can be found in the text, so making it understandable and processable by computers. There is this model called BERT. I don't know if you guys read this paper called Attention is All You Need, but basically that's kind of like the birth of this transformer revolution. So models like BERT are trained on a vast amount of text, learning to understand the integrate relationship between words and the subtle nuances of meaning that make language rich and expressive. So how do they work? How's the process? So The transformation from text to vector starts with this thing called tokenization. So every time that you work with these models, it can be ChatGPT or Llama, you're gonna see like tokens. So the process starts with tokenization, and in this step, sentences are broken into smaller pieces that are called tokens. And these tokens representing words or subwords, and they're fed into the sentence transformers. And as they pass through various layers in the model, each token is translated into a numerical form, creating a vector that holds the token's semantic value. And each layer of the model captures different aspects of the text, weaving the context individual meaning into a cohesive multi-dimensional vector that reflects the text overall context. So every time that you go from layer to layer to layer, you are adding more values and more meanings to the token, so you can create more relationship and find more similarities. And then we go to the next slide where we're going to talk about this similarity and why it's really important. But first, at least in this code that I wrote and where I wrote, and where I'm doing the examples, I'm using PostgreSQL that I'm pretty sure that everyone knows, but like PostgreSQL is an advanced enterprise class open source relational database that supports both SQL relational and JSON no relational querying, making it like very versatile choice for many types of applications. But in this case, we need to add a little extension that is called PG Vector that we are using in this example. So PG Vector turns PostgreSQL into a powerful vector database, enabling efficient storage and rapid query of high dimensional vectors. So it introduces new data types and indexing methods that are specifically optimized for vector data, and it enhances PostgreSQL performance in vector similarity searches. So when we're talking about vector similarity searches, we have this algorithm called KNN, which means K nearest network, K nearest neighbor, not network, neighbor. So this is an algorithm that is like, I would say like a virtual detective that is super quick and efficient at finding things that are similar. So each piece of the data is like a point in space, and similar data points are close to each other. So you have a specific data point or a query, and you want to find other points that are similar to it. So this algorithm quickly scans the data and identifies and predetermines numbers of points. So these are like K points, they are called, and they find the ones that are closest to your query. So it is not about physical proximity, for example, two words that look very similar, but it's about how similar the characteristics and or features are, ensuring that these points are not just close, but they are also meaningful matches. So I have here. Sorry? Hello? I can't understand. So I have here a comparison between three embedding models that I tried in this example. So one is from OpenAI that is called ADA. And then there are two that I tried from the Beijing Academy of Artificial Intelligence. It's a Chinese embedding model. One I would consider a bad embedding model, but then there is one that is supposed to be better, an enhanced version that is optimized for higher accuracy and richer semantic capture. So the OpenAI embedding has a characteristic that I consider that is very important, that it has a very big amount of tokens that you can have per embedding. So when you retrieve data, it has like access to more information. So that's interesting. And when I go to the models from the Beijing Academy of AI, the ones that I'm using are the base 1.5 and the base that is like at the end. But if you can see the numbers, they are actually really similar. But now I'm gonna show the results. So what I did is that I run this piece of text. This is a story that I wrote. This is just the first page, but my story is like, it's like 6 or 7 pages. Very interesting. If you guys want to read it, ask me and or maybe I'll put it in my folder in Google Drive. So this is a story. It's called The Robot Who Discovered Love. And then I ran the story through the embedding algorithm and I stored it into a vector database. And I did it 3 times. I did it once with each model. And then I asked a question to the language model. For the ones that I use the Beijing embedding model, I use Llama. And for the OpenAI, well, I use GPT-4. So in the first case, you're going to see that the model was the base model. It took to create the embeddings a little bit less than 10 seconds, 9.77 seconds, and it created 97 records in the table. I created this table, called robot BAAI. And when I asked the large language model, what is the name of the robot, which is like very simple to retrieve, he extracted this relevant information from source, this piece of text, and then he responded, the robot's name is MX174B, which is not correct. You see that the robot responds, I am a robot. The robot replied, I don't have a name. My model is. So he's saying the robot's name is the model. So the answer to the question is not correct. So then I decided, okay, what if I upgrade to this model that is the supposed to be one of the top models? The 1.5 version is ranked among the best. Is ranked among the best in terms of performance. So I did the same. I created a new table using the model, which the table is called robot BAAI B1.5 or 1.5. The PostgreSQL doesn't allow me to put a point in the name. And I asked the same question. It took a little bit longer than 10 seconds to create the embedding. In this case, it was longer, this model, to create embedding that was the previous. And when I got the response, it took 62 seconds to respond, and he also got the name wrong. So there was no improvement here. But then I decided to conduct a different experiment. And I thought, what if I use the new model?
But if you look at the data which was returned from the database, it's very similar, right? And it says what?
Okay. But now I decided, let me do something different. Let me use this model, but let me use it with the table that has the embeddings created with the previous model. And this is like really crazy, but I just did it to try. And for some reason that I don't understand, got the answer right. And the response time for the Llama also was shorter, only 46 seconds in my computer that I don't have a GPU. He got the name of the robot is Max. So he got that part right. Why? I don't know why, but he understood it. I did the same question to OpenAI, and OpenAI got a very big chunk of text because he can, and in a little bit more than 2 seconds, and he created the table also in 2 seconds. Got that the name is Max. So why that happened? I don't know. I really don't know, but for some reason, when I did that mix from one model to the other model, it got the answer right. So I believe that there is more experimentation that we have to do in order to get
Elias,
to make this work.
can
Mhm.
you go back to the first model and show what data it found? Did it even find the word max in it?
No,
Uh, oh, okay. So that's why. So retrieval from the database, the similarity search itself didn't return the max.
yes, but the similarity search with one model to the other, apparently it did return the max. Because the name of the model was MX174B and it had like MX. So in the story, the woman said, well, if your name is MX, I'll call you Max.
Okay, and when we were doing similarity search, have you tried different metrics for similarity, or you just use the default, which I think is cosine similarity?
I used the default.
Okay.
I haven't tried, I haven't gone that deep. I can show the code and we can run the queries again if you guys want to see it.
No, not now. Okay.
Hmm. Oh, I'm sorry. I believe that the problem is that if you see this first approach returns three sentences, and this is default in our sample code, return three nearest points, right? But once you call, could you scroll down?
You talk OpenAI, yeah, OpenAI returns a lot of.
Yeah, OpenAI returns the sentence, right? No, one up.
One up is not OpenAI.
No, not an OpenAI. One up. One slide back.
Elias, can you move? Yeah. Okay.
Yeah, you see, there is a fourth and fifth sentences. Returned, which will contain right information, correct?
Yes.
Yeah. So, but you said that construction of vectors was performed by just base model, right? And
Yes.
retrieval was performed but with version 1.5.
Yes. For some reason, when I did it that way, it gave a correct result, and I don't know why.
I
Maybe it's
don't
a
know.
mistake.
Yeah. In addition,
Maybe it's a mistake.
I would also check. Maybe the last two sentences, even divided by empty, carriage return, right? Empty line. Because or maybe you didn't change number of returned information. So you see this number of returned sources from database, because I believe that in our samples it was just limited by 3.
And here it looks
I
like it's
also
5.
think I also think that maybe if we increase the size of the chunks, we might have a better
Yeah.
chance to get it right.
Right.
Because
Yeah, absolutely.
because I mean, if the model cannot retrieve like what is the name of the robot, like how are you gonna respond something more complicated into like a business scenario where you want to retrieve something that is actually complex?
In most of the business scenarios, text is much more structural than in, poem about love. Right?
Well, like
And
this is what is your name?
but the robot actually replied, "I don't have a name," right? And
But then the woman gives him a name.
yeah, but it is uh, she never stated that this is a name. This concept run through several sentences and always change their form, right? So that's pretty much expected. So
Yes, but
Okay.
Llama does his job well.
right,
Llama
Yeah.
understands and responds well. So the problem is with
right,
the
but
retrieval.
and here also it runs well, you know. And if you can do the same experiment when you said found relevant information from the source, and there are different relevance numbers, right? So it will give you pieces of text, right, with relevance idea. So if you can print it, just trace it the way, number one, the robot who discovered blah, blah, blah with relevance, I don't know, 55% or whatever, right? There should be just a number, right? And then next one, next one, next one. Maybe we can see, trace it this way. We can see what's wrong with the first one.
Great idea. Yeah.
Because this is definitely, something not really wrong with the model, very likely, but the way we treat the results. And so we'll see one by one.
Right. Elias, this is the end of your presentation, or you have more?
No, that is the end.
Oh, that's the
Okay.
end. Okay, then I'll stop recording just a second.